Hello, everyone. In this video, we'll be going over the mathematical structure of quantum information in relation to vectors, their spaces, and how they can be transformed. To start, a vector is a mathematical object that has both a magnitude and a direction. Consider this red arrow here. This is its head, and this is its tail. The length of the arrow represents the magnitude, and the direction in which the head is pointing represents the direction of the vector. In quantum information, the mathematical quantity that's analogous to the length of a vector is always equal to 1. In linear algebra, the spaces in which vectors live, called vector spaces, are the basic geometric objects studied. In this graph, we have a two-dimensional space spanned by the two vectors in the x and y directions, ex and ey. Here, our basis consists of these two vectors called basis vectors. Our vector v, depicted here by the red arrow, can be written as a linear combination of ex and ey, with a being associated with ex and b being associated with ey. Remember in the last slide we said that in quantum information, the length of v is always equal to 1? Well, a consequence of that is that the absolute value squared of a plus the absolute value squared of b equals 1. We're using absolute values because in quantum information, a and b are not always real valued. Orthogonal bases, such as those consisting of ex and ey, are very convenient to work with mathematically. Orthogonal meaning that if you calculate the dot product of two different basis elements, you get 0. So what do you do if you find yourself with non-orthogonal vectors? Well, there's a way you can redefine them to make them orthogonal and re-express your vector in terms of this new orthogonal basis. So here we have two non-orthogonal vectors, u and v, with angle theta between them. Let's find the projection of v on u. With some trigonometry, we find that the length of that projection is equal to the absolute value of v times cosine theta, and of course it points in the u direction. Now let's subtract this projection from v using the famous head-to-tail method. Since we're subtracting the projector, we have to give it a minus u direction, then up the v vector. The resultant is this red vector, which is perpendicular to u, so we call it u perp. The length of this vector is the absolute value of v times sine theta. So we got ourselves the two perpendicular vectors u and u perp from the original non-perpendicular vectors u and v. This is where the Gram-Schmidt orthogonalization method, used a lot in quantum information research, comes from. What can we do to these vectors? Well, we can transform them. We will look at a couple of isometric transformations because these kind of transformations are analogous to unitary transformations in quantum information. And quantum gates, which are operators applied on the building blocks of quantum computers, are represented by unitary matrices. Here we have a point P. A reflection in the x-axis gets it reflected to the other side of the x-axis. This is how the transformation is expressed in terms of matrices. The value of x stays the same, but that of y becomes the negative of the original. And this is the matrix that represents reflection in the x-axis. In quantum information, this matrix is called a Z-gate, which is easier to implement compared to other gates in the creation of quantum entanglement, the star resource in quantum information. Another isometric transformation is the rotation. Again, we have point P. The vector representing it starts from the origin and goes all the way to P. That vector makes an angle theta with the x-axis. Let's rotate it by an angle phi. The position of P changes to P prime, but the length of the line doesn't change. So x goes to x prime and y goes to y prime. Here's the matrix representation of this transformation, and this is the rotation matrix. A related matrix from Qi is the Y-gate. I want to leave you with an exercise which can be rewarding if you do it. Derive this rotation matrix using trigonometric identities. Bye for now.